Example 1.3 Equilibrium position. Two charged particles are placed as shown in the figure. Q1 equals 0.15 microcoulomb is located at the origin, and Q2 equals 0.35 microcoulomb is located on the positive x-axis at x2 equals 0.40 meter. Where should a third charged particle Q3 be placed to be at an equilibrium point such that the forces on it sum to zero? So here you have two charged particles Q1 and Q2 with magnitude of charge Q1 is equal to 0.15 microcoulomb, and 0.15 microcoulomb we can write as 0.15 times 10 to the power negative 6 coulomb. Same with charge Q2, which is 0.35 microcoulomb. That becomes equal to 0.35 times 10 to the power negative 6 coulomb. Position of charge Q1 is given as x1, and x1 is at origin, so we write its position to be equal to 0, whereas charge Q2 is placed at x2, and x2 is given as 0.40 meter. We need to find where can we place a third charge Q3 such that Q3 is at equilibrium. Equilibrium means sum of all forces acting on that charge is equal to 0. Now, how do we determine where do we place this charge? If the given two charges are like charges, that means if they are both either positive or both are negative, then the third charge has to be placed at a point in between the two charges. So since here Q1 and Q2 are both positive, I will place my third charge somewhere in between them. And this third charge always has to be closer to the charge which is smaller in magnitude. So out of these two charges, whoever is smaller in magnitude, I will place my third charge closer to them. And if they were equal in magnitude, the third charge will be placed exactly at a point midway between them. So I will call this charge Q3, and Q3 is closer to Q1, as in the given question Q1 is smaller than Q2. If these two charges were unlike, that means if I had a positive and a negative charge, the third charge had to be placed outside of these charges at any point outside of them. And it will always be closer to the one who has a smaller magnitude. So if Q1 is smaller, the third charge had to be placed outside of Q1. And if Q2 was smaller, we will place it to the right outside of Q2. Here in the question, the charge Q3 is negative, but irrespective of its sign, no matter what kind of charge you choose, the answer remains the same. So let us sketch all the forces acting on charge Q3. Q3 is negative, Q1 and Q2 are both positive. So because of charge Q1, Q3 will be attracted to Q1, and the force acting on Q3 because of Q1 will be to the left. We will call this force F of 1 on 3. Same with Q2, because of Q2, Q3 will be pulled to the right, and we call this force F23. For charge Q3 to be at equilibrium, the two forces acting on it must be equal in magnitude and opposite in direction. So we can write their magnitudes to be equal. F13 will be equal to F23. Now from Coulomb's law, electrostatic force between two charge can be given as K Q1 Q3 over R13 squared, which is equal to K Q2 Q3 over R23 squared. Now here we can cancel the common terms K and K as well as Q3 and Q3, and let's write down whatever is left. You're left with Q1 over R13 squared equals Q2 over R23 squared. Now R13 is distance between charge Q1 and Q3. Let the position of Q3 be given as x3. Distance between Q1 and Q3 is R13, and we can write R13 to be equal to x3 minus x1. Now here x1 is at origin. The position of x1 will be equal to 0. So when you do x3 minus x1, you are basically only left with x3. So distance between q1 and q3, which is r13, can be just written as x3. Same with r23. R23 is the distance between q3 and charge 2, and we can write r23 as x2 minus x3. We are just taking the difference in position for them all. So let's substitute this value. Q1 over R13, which is x3 squared, equals Q2 over R23, which is x2 minus x3 squared. So before we solve further, let's take the square root. I can write square root Q1 x3 equals square root Q2 over x2 minus x3. Now we know what is Q1, Q2, and x2. We need to find what is x3. So if you do not wish to solve any further, you can use shift solve at this point to calculate x3, or else we can rearrange the term to solve for x3 as follows. You can cross multiply the terms over here, and we get square root q1 x2 minus x3 to be equal to square root q2 times x3. Now bring the terms with x3 together and q together. So I will write x2 minus x3 divided by x3 to be equal to square root q2 over q1. Then we solve further. X2 over x3 minus x3 over x3 will give me 1 equals square root q2 over square root q1. Now move 1 to the other side. You get x2 over x3 to be equal to square root q2 over square root q1 plus 1. Now solve the mixed fraction over here. We get x2 over x3 to be equal to square root q2 multiply with q1 over square root q1. Then we cross multiply to solve for x3. I will take x3 to the top here, bring root q2 plus root q1 at the bottom, and take this on the top here. So we get x3 to be equal to x2 root q1 over root q2 plus root q1. Now substitute. We get x3 to be equal to x2 is 0.4, square root q1 is 0.15 times 10 to the power negative 6 over square root q2 is 0.35 times 10 to the power negative 6 plus square root q1 is 0.15 times 10 to the power negative 6. And when you solve this, you get position of charge q3 to be equal to 0.158, which you can round off to 0.16 meter. So this is the position at which you will place the third charge such that it remains at equilibrium. That means the forces acting on it sum to 0.